Okay, today we're reviewing exponential functions for pre-calculus. This is a topic that you covered in fair depth during advanced algebra, and we're reviewing it. So step one is what makes something an exponential function? What's the feature we're looking for that makes it exponential?
It creates the power of x.
Good. In other words, if we have something like y equals 2 to the x, or y equals 3 to the x, or y equals 1/2 to the x, or even y equals e to the x, because the x exists in the exponent, it's called an exponential function. When we graph these, there's something common that all of these have. If I'm going to graph the parent function, for instance, in this case, y equals 2 to the x, what I'm going to think about is an xy table. And I'm going to start with the easiest one, which is a 0. What is 2 to the 0th? 1. So in other words, I've got the point 0, 1 on my graph. Would that point also exist in this graph? Because 3 to the 0th is also 1. What about 1/2 to the 0th? What about e to the 0th? So this point is a common anchor for all of our parent functions. When I then go to the first power, and I'm saying 2 to the first, that's going to give me 2. Or in this case, be 3, in this case, be 1/2. It changes. Now is when it begins to adapt a little bit to the base. 2 squared is 4. What happens when I go negative? What's 2 to the negative 1? 1/2. And what about negative 2? 2 to the negative 2? 1/4. 1/2 squared, which is 1/4. And we end up with this telltale curve. Is this called exponential growth or exponential decay? Exponential growth. And it rockets up at a fast rate. What are some examples in life when we care about exponential growth? Population, good. Investing, nice. Over time, the longer your money's in place, the better value you'll get. In terms of population growth, there's an old example. Let's say that you're trying to fill a 2-liter soda bottle. And first you put in 1 bean, and then you put in 2 beans. And then you put in double that, 4 beans. And then you put in 8 beans. And let's say that it takes, 30 days to be completely full. How many days until it's half full? Yeah. Doesn't that sound odd? Most people want to say it 15 days, halfway through. But because it's a doubling function, the immediately prior to last day is when it was half as full. And when you double it, it becomes full. That's why with population, with global climate change, we have to be concerned about an environment that is exponentially growing, because it could be too late before you know it. Anyway, off my soapbox. What if I wanted to express something like y is equal to negative 1/2 2 to the x plus 2 minus 3? It's a transformation. And you look at the parent function, we're still talking about this parent function. And then we're going to talk about the transformations. What are the transformations associated with the x? Left 2. Even though it says plus 2, we're going to do the opposite of what's inside there, right? What about the transformations associated with the y? Down 3. What else? It's a reflection. And if the y values are being multiplied, it's a reflection over the x-axis, right? And what's this part? So it's a vertical compression multiplied by 1/2. And an easier way to think about this is to actually make a table of values for this. What happens to the x values? We're going to take all these x values and undertake a transformation. What happens when we say left 2? We're going to subtract 2 away, right? We're going to do the opposite of what's going on here because it's in with the x. If this is x plus 2, we're going to subtract 2. What about the y? What transformations will we undertake with the y value? I'm going to subtract 3 and multiply it times -1/2. So now I'll just apply each of these values. Instead of the point -2 1/4, I'm going to take my x value and subtract 2. So -2 minus 2 is -4. And then -1/2 times 1/4 y minus 3 is, oops, that is the y, is equal to -3 1/8. And then I'll do it for -1. -1 minus 2 is -3. -1/2 times 1/2 minus 3, -1/4 minus 3 is -3 1/4. Then I'll do it for 0. 0 minus 2 is -2. My corresponding value is 1. -1/2 times 1 minus 3 is going to be -3 1/2. 1 minus 2 is -1. And my y value is -1/2 times 2 minus 3. That's -1 minus 3 is -4. Now we're moving. 2 minus 2 is equal to 0. -1/2 times 4 minus 3, that's -2 minus 3 is -5. There's one more important thing that I should have included in my parent function. Do we have any asymptotic behavior in this?
Oh, yeah.
We do. What's the asymptote? What's the equation for it? Y equals 0, right? This line, the x-axis, is asymptotic. We're getting really, really close to it. We're never going to have it go negative. We're never going to have it achieve actually 0, but it is approaching 0. And I'm going to use that same thing over here when I do my transformations. Is there any x component to this? No, it says y equals 0, but there is a y component. So I can apply this same transformation to y equals 0. What happens if I take -1/2 times 0? 0, and then I subtract 3. So I've got an asymptote at y equals -3. So to graph this function, I'm going to go 1, 2, 3. Here's my asymptote. And then I'm going to begin to apply the points. At 0, it's at -5. At -1, it's at -4. At -3, it's at 3 1/2. And it's getting closer and closer and closer to that y equals -3 asymptote. It's going to look like that. How would this change if I had like y equals 3 to the x? Would it look kind of similar to this? It would. It would just be a little bit more extreme. Instead of going over 1 up 2, it'd go over 1 up 3. Instead of over 2 up 4, it'd go over 2 up 9. -1 1/2 versus -1 1/3. -2 1/4, -2 1/9. What about this one? What would that look like? Can we, that doesn't show up very well, does it? Can we treat this as a transformation?
Yeah.
We can. Can't we call this y is equal to 2 to the -x? Right? Because 2 to the -1 is the same as 1/2. And so what that's going to do is it's simply going to swap all the x values. And what we'd end up with is still the 0.01, but now our 1/2 comes over here, our 1/4 comes over here, our 2 is over here, our 4 is over here. And we see this as exponential decay. Any questions? What would it look like for y is equal to e to the x? What would our coordinates be?
Oh, really?
They would, which wouldn't help us much to say, oh, we can't express them as anything. So how do we express them? Yeah. What happens at 0? If I put in a 0 here, what's e to the 0th? 1. And what's e to the first? E. So when I'm labeling the point, I'd want to label this 1 comma e. but realistically, I'd put it on about 2.7. -1 would be 1 over E. That's the exact value. So when I label it, I'd want to put -1 comma 1 over E. And in terms of graphing it, what's an estimation of 1 over 2.7? Something like 1/3-ish. Maybe that resonates for you. This would be about 1. I bet it's more like 1/8. Let's see. E to the -2. And then if I did 1 divided by 8, yeah, that's closer. What's 1 divided by 9? 1 divided by 7? No. Yeah, it's between 1/8 and 1/7. And so if I were to graph 1 over E, excuse me, E to the X, it would still have a point of 0, 1. And here its first point would be 1 comma E, and its second point would be 2 comma E squared. -1 would be -1 comma 1 over E. It would look something like that. Okay. Now, we're going to be using these graphs with transformations, but the whole point of this is the ability to solve, predict, and extrapolate. In other words, solve problems. So we're going to be dealing with exponential growth and decay. And you may remember that there's 2 primary formulas we're going to use. One does involve E, hert, and one doesn't involve E. What's the difference between these? Oops. Hard to see, but that's an R there. Okay, so let's take this one for example. This is something that we might use with investing. If I have $1,000 that I want to invest, and I might get 5% annual interest rate, and I want to put it in for 20 years, what's it going to be worth? One more feature. What does the N refer to? Not quite. T refers to the number of years. R is the rate. What's the 1,000? P, our principal. N is the number of times we get paid interest. How many times each year do we get paid? And normally you'd get paid every year. That means they only have to apply this once each year. Ideally, you'd want them to do it quarterly or monthly or daily. That'd be great. Then you get a whole bunch more money over time. So in this case, let's go with monthly. So if I were setting this up, I'd look at A. What does the A mean? Like the answer, right? Or the after amount at the end. So it'll be 1,000 times 1 plus what? Most. Good, 0.05 over 12. Now, 0.05 is our interest rate. If we take 5%, I change it into 0.05 as a decimal. What am I doing when I divide it by 12? Good. I'm splitting up my annual interest rate into monthly interest rates. If it's 5% for the whole year, dividing it by 12 gives me how much interest I get every month, which means up here, I don't want to put in years because I'm not getting paid just 20 years. I'm getting paid 12 months times 20 years, so 240. And if I plug this into a calculator, see what 0.05 divided by 12 comes out to be. That's that decimal. Why am I adding 1 to it? Almost. Yeah, because I get back my initial money, right? I'm not just getting the interest rate. I'm also getting 100% of my initial money plus the interest rate. So this would be 1.0041666 to the 240. And so in my calculator, I'd do 1,000 times that last answer raised to the 240. And that would give me $2,712.64. Any questions on that? Could you solve this kind of problem instead by saying, if I have $1,000 and I'm going to put it in for 20 years, what would interest rate have to be to give me $2,700? Yeah, you just move the variable around, right? Instead of it here, you'd have a variable here and you'd have to unravel it. What happens if the question asks for time? How long would it take? Well, let's ask it this way. If I took a totally different question, like 2x equals 8, how do you solve that? Divide by 2, because it's being multiplied. The opposite is divide. What if I took x plus 6 equals 10? What would you do to solve that? You'd subtract 6, because you're adding 6. Adding and subtracting are opposites. What if I had x squared equals 20? Sure, because the opposite of squaring is square root. So what if I had something like x as an exponent? There isn't an x root. Instead, we have to bring in logarithms. So this unit is going to be about exponential growth decay and logarithms. Today's work doesn't involve logarithms. Today is just going to be solving problems without solving for t. What is the e in this other equation? Why would we use this instead of this one? You've been doing a great job, Jason. Let's get some other voices. What is this for? Good. Natural log. E, the natural constant, exactly. When we do this one, we're using our artificial construct of time, right? Months, days, hours. These are all things that we as humans invented. And so we created a formula that fits that. It's very regulated. But it turns out that bacteria don't have watches. And so when they're doubling in real life, or when we're looking at exponential decay or growth from radioactive substances, they don't follow our timeline. They use this naturally doubling constant. And so if we had something like, for example, strontium, I don't remember the number, but one of the radioactive elements, they would tell us its half-life of 2,000 years. And then we want to find out how much of a 20 milligram substance after 16,000 years. No, that's too easy. After 5,000 years. When you do these problems, it's a two-stepper. First, you have to find the rate of decay. So if we have a half-life, what does that mean? It lost half of its value. So what would be a relationship between the initial amount and the later amount such that it's losing half the amount? Maybe we started with 10, in which case our after would be 5. Maybe we started with 2 and our after would be 1. Maybe we started with 100% and our after would be 50%. It doesn't matter what you choose. Whatever values you pick, the after amount has to be half of the initial amount. We don't know the rate. We're looking for a half-life value being 2,000 years. Your first step would then be to divide by 2, and every single time, no matter what pair you chose, you'd get 0.5 is equal to e to the r times 2,000, the half-life. And now, again, we're not going to get into too many logs at this point, but since it's up in the exponent, we'd have to solve this. What do you do to solve this? You'd have to apply a natural log. You'd bring the e down, you get log base e of 0.5 equals 2,000 r, which is the same as ln of 0.5 equals 2,000 r. What do you do to solve for r? If I plug that in, I would get the rate necessary. Once I get that value, then I'd come back and do my problem again, now with that new rate value, plugging in a t of 5,000, initial principal of 20, and my new rate, and I'd be able to find my A. I think this should give you what you need for today's work. You've got the period.